Hello everyone, I'm Timali Malinia from the Department of Physical Sciences, Faculty of Applied Sciences, Rajaratnam University of Sri Lanka. Today, I will be presenting my research on the topic Rainbow Connection Number of k-Petal Triangular Flower Graphs. Here is the content of what I will be covering today. Let's move on to introduction. Graph theory is a branch of mathematics that studies relationships between objects, where we represent objects as vertices and the connections between them as edges. And together, these form a structure called a graph. Despite this simple foundation, graph theory has become one of the most powerful tools in modern mathematics and computer science, appearing naturally in road networks where cities are vertices and roads are edges. In the internet, where devices are vertices and connections are edges. And even in social media platforms, where people are vertices and friends are edges, meaning any system involving relationships or connections can be modeled as graphs. One important area within graph theory is edge coloring, which is the process of assigning colors to the edge of a graph in order to study how connections in a network can be distinguished from one another. And from this area emerged a particular interesting concept called rainbow connection. A graph is said to be rainbow connected if for every pair of vertices there exists at least one path between them, where no two edges share the same color. Such a path is called the rainbow path, and the minimum number of colors needed to achieve this property across the entire graph is called the rainbow connection number, which is denoted by RCG. This concept carries a significant real-world importance. In network security, a rainbow path ensures that a message travels through a sequence of completely distinct communication networks, making it significantly harder for an attacker to intercept the full message. While in communication networks, rainbow connections help design systems where signals travel through unique, non-repeating pathways, reducing interference and improving the overall reliability of the network, which is especially critical in wireless sensor networks. Beyond engineering, rainbow connection has deep relevance in combinatorics and theoretical computer science, connecting to problem in routing, fault tolerance, and channel assignment, areas that are central to the design of modern networks and distributed systems. And it is within this rich theoretical and practical context that the present research investigates the rainbow connection number of a specific and structured graph family known as the k-Petal triangular flower graphs. Let's move on to research objectives. My research has 5 clear objectives. First, to determine the rainbow connection number of k-Petal flower graphs. Second, to analyze the path structure within these graphs to understand how paths traverse through petals and the central vertex. Third, to provide a rigorous mathematical proof establishing the exact rainbow connection number. Fourth one is to investigate scalability, specifically how the rainbow connection number behaves as the number of petals k increases. And finally, to develop a coloring algorithm that achieves Rainbow connectivity using the minimum number of colors. Problem statement. The scope of this study focused especially on the k-Petal triangular flower graphs, a structured and systematic class of graphs where k-petals are attached to a single central vertex. This is a well-defined and tractable graph family that makes it ideal for exploring rainbow coloring properties. In terms of relevance, this research continues to the growing theory of rainbow coloring by working with a class of graphs that haven't been fully characterized in this context. It adds a meaningful result to the existing body of knowledge. The central research question driving this to what is the minimum number of colors required to make a k-petal graph rainbow connected? This is the question my proof aims to answer. Let's move on to methodology. My methodology follows a structured mathematical approach. I began by formally defining the k-petal triangular flower graph. I identifying its vertex set and edge set. The graph consists of a central vertex V0 and k-petals, each petal forming a triangle with the central vertex. From there, I analyze the longest simple path in the graph to determine the diameter, which gives a lower bound on the rainbow connection number. Then I constructed an explicit coloring scheme and verified that it achieves rainbow connectivity. Finally, I proved both the necessary and sufficiency of the proposed number of colors, meaning I showed that fewer colors are not enough and the number I identified is exactly enough. Let's move on to literature review. The study of rainbow connection in graph began with the foundational work of Chartrand and all his colleagues in 2008, who formally introduced the concept of rainbow connection, defined the rainbow connection number RCG, and established the fundamental result that for any connected graph G, the rainbow connection number is always greater than or equal to the diameter of the graph. A cornerstone inequality that subsequent researchers built upon and that directly informs the lower bound arguments used in the present research. Building on this foundation, Lee and Son published a comprehensive survey in 2012 that documented rainbow connection results across a wide range of graph families, including paths, cycles, wheels, and complete bipartite graphs. And importantly, identified open problems that guided from research, highlighting that while many simple graph families had been characterized, a large number of structured and symmetric graph families still remain unexplored, providing the motivation for studies such as the present. Let's move on to k-Petal flower graph. Let me now describe the graph structure more precisely. A k-Petal triangular flower graph has a central vertex V0 at its center. Attached to this central vertex, there are k-petals. Each petal contains vertices labeled as Vij, where I denotes the petal number from 1 to k and j denotes the position within the petal from 1 to n. In the triangular case, each petal forms a triangle connected to the central vertex through what we call spoke edges. The outer edges of each petal connect the petal vertices to one another. Proof that three colors are necessary and sufficient graph structure. The graph consists of several petals sharing a common central vertex. Each petal forms a triangle. Longest simple path. Any path between different petals must pass through V0, which is center vertex. The longest simple path is as I mentioned here. Path length is 3 edges. We need at least 3 colors. A rainbow path of a length 3 requires all edges to have distinct colors. Hence, at least 3 colors are required. Sufficiency of 3 colors. Steps. Color all outer edges with color 1. Color spoke edges with color 2 and color 3. Starting from any spoke, move clockwise or anti-clockwise. Alternate colors, color 2, color 3, color 2, color 3, so on. All vertex pairs are connected by a rainbow path within petals and between petals. The minimum number of colors required is 3. Let's analyze the petal graphs. I verified this result for specific values of k. For k equal 3, 4 and 5. As shown here, the coloring scheme works correctly in all cases and 3 colors suffice regardless of how many petals. This visual confirms the general proof. Results. First finding is maximum path length. The longest simple path in any k-petal flower graph has exactly 3 edges, occurring when traversing from one petal to another through the central vertex V0. Second finding is independence from number of petals. The rainbow connection number is 3 and independent from number of petals. Third finding is efficient coloring. A simple 3-color scheme achieves optimal rainbow connectivity. Conclusion. First one is successfully determined chromatic number is 3 for k-petal flower graphs. Second one is result is independent of number of petals. Third one is provided complete rigorous proof. Fourth one is designed efficient 3-color edge coloring scheme. These are the references I used to study. That brings me to the end of my presentation. Thank you very much for your time and attention.